Okay, good morning, Astronomy 1020. We're back after a couple of technical glitches this morning. Hello, Amy. Uh, it's our final lecture today. Woo! We've completed the class. And so today is sort of a victory lap where we learn about some fun things. Figure I'd talk a little bit about general relativity, which I didn't quite get to in our relativity lecture. And that will make for a nice segue into discussions of black holes, which are also part of this week's lecture. I do have a homework that I've planned for us today, but I have not posted it yet. I have a homework listed in the syllabus for chapter 19 on the Milky Way, and I may still assign a few of those problems. It also could be cool to pick some problems from relativity or from the stellar death section. I haven't quite decided yet. So I think during the tea break, I just want to take one last look at things so I can modify them. And I wanted to this morning, but things get out of hand. Okay, Julie is logging in from work.
I'm back.
Back. I'm back too. Okay. Okay, so announcements before I begin. I need to finish the grading for this class. I've actually caught up with this class's grading. I think it's just this week's work that I have to contend with. So I've got to grade the lab from Tuesday, and I'm going to have to grade whatever homework we do today. I'd like to do that on Sunday and kind of have this wrapped up by next week. Does that seem reasonable to the few of you who are here with me? Okay. Hopefully that will be reasonable to the viewers who are watching later from the comforts of their couch. It can't go on forever, right? Most of us have opted not to take the midterm, not to take the final, but to double our midterm grade, which is a nice, easy way to end the semester, low stress. If anyone does want to take the final, you have a right to take the final, and you should contact me about that. Otherwise, I'll assume you want to double your midterm grade and be done with it. However, I cannot keep the semester open forever. So like by Monday or maybe Tuesday latest, I'm going to try to calculate everyone's grade and submit that. And hopefully that seems like a reasonable amount of time. Probably when you guys log out of your computer today, you'll just be done with it, and that'll be fine for you. I have other bad news about student ratings of instruction. For some reason, I missed the deadline to do student ratings of instruction. But that's very bizarre to me because I'm kind of old-fashioned. So when I teach a class in person, I normally give those student ratings of instructions as a paper handout, and I kind of force everyone to sit there and evaluate me. So I'm kind of used to doing this on the last day of class. And yesterday I discovered that they deactivate the SRIs the week before the last week of class. That doesn't really make a lot of sense to me, but that means I don't think you're going to be able to evaluate me, and I'm very sorry about that. I actually do enjoy hearing your opinions about the class. I suppose you could write me email or an angry email if you'd like. But unless I send you a follow-up email, I don't think you're going to be able to do that. I'm sorry. It's just an irrational design of the system here at CCRI. Okay. Let's talk about general relativity. Do you guys remember what the postulates of special relativity were?
The speed of light is a constant.
Yep.
The laws of physics are the same for all observers in their frame of reference.
Pretty good. It almost makes a kind of sing-song, Vladimir. That's how you're supposed to remember it. The laws of physics are the same in all inertial reference frames. But you pretty much got the right idea, okay? Special relativity was proposed by Einstein in 1905. And what makes special relativity special is basically one concept. That concept is the inertial reference frame. All observers have to be traveling at a constant velocity. And if they travel at a constant velocity, times will flow at different rates, lengths will contract, masses will change, simultaneity does not hold in all reference frames. All the weird consequences that you guys discovered when you listened to that lecture. But of course, there is no such thing as a constant velocity. If you step into your car, you have to accelerate to go from 0 to fast, and it becomes very difficult to maintain a perfectly constant speed. Also, any rotations at all have accelerations built into them, such as the centrifugal force, the Coriolis force, all these other accelerations that even just rotating in a circle itself constitutes an acceleration. So since we're on a rotating Earth, and Earth rotates around the sun, and the sun rotates around the galaxy, there sort of is no such thing as a constant velocity. And yet we have observed in the laboratory effects of special relativity. Time dilation is real. Just remember that experiment, not the Pound-Rebka experiment, but the experiment where the two scientists traveled on the plane and measured the rate of time different at those two atomic clocks. The Hafele-Keating experiment. Sorry, I blanked on it for just a second. Einstein knew that if accelerations were involved, obviously the effects of relativity would still hold. But to craft a theory of it was going to be much more mathematically complex. Weirdly, when Albert Einstein set out to do something, he actually accomplished it. And 10 years later, he had formulated a new theory in 1915 of general relativity. Whereas the original idea for general relativity was to develop a theory of motion to include accelerations, what it ended up becoming, maybe even by accident, was a new theory of gravity. And in fact, today, the theory of general relativity is our dominant framework for how we understand gravitational forces. We've since disproved, if you will, Newton's law of gravitation. It's not sufficient to explain all circumstances. But because Newton's law of gravity explains the vast majority of gravitational effects, we haven't thrown away Newton's law of gravity. We've held on to it as a law, something that is technically not true, but is so useful in so many different circumstances that you might as well keep it around. Theories are things which have never been disproven. And the theory of general relativity is a more complex theory of gravity than Newton's law, but you don't always want to bust it out unless you absolutely need to. When do you need to? Well, when you pack a whole lot of gravity into a very tiny sphere. You guessed it, black holes are the perfect time to talk about general relativity. In fact, even neutron stars are as well, because you guys saw last class that the typical escape velocity of a neutron star is
79% speed of light.
right. And that's no joke. At those kind of escape velocities, actually, the theory of general relativity is probably what's necessary. I sort of tiptoed around those, around the edge of the neutron star, because I wanted to save it all for today. Okay, so how do we get going? We're going to need to start with a postulate. Unlike special relativity, which has two postulates, GR has one, and it is known as the principle of equivalence. So the one postulate that dominates the theory of general relativity is called the principle of equivalence. And it has many elaborate constructions, but it's actually, at its biggest picture, a very simple idea that the effects of acceleration due to motion are equal in every respect to the effects of gravitational acceleration. And I'll elaborate on this with some pictures in a moment. In fact, if this was too long, didn't read for you youngsters out there, then maybe we could even make it stupider, okay? We could make it simpler. That acceleration is equivalent to gravity. That's kind of a lame way to say it, but it's basic idea. Okay. Let's start by taking a peek at one of our slideshows so that you guys can understand what this all means. And to do this, I'm going to go to my relativity section, fast forward to the principle of equivalence. And in slide 41, you can see sort of two different scenarios which could be described by the principle of equivalence in the same terms. Normally, students who sit inside of a classroom feel the effects of gravity, whether you realize it or not, pinning you to the floor of the classroom. The fact that you cannot jump off the Earth into outer space means that there is a force which is pinning you down to the ground. You're used to dealing with it every day, so you're not really conscious of it. Astronauts who go to space and experience low G environments, weightlessness, when they come back to Earth, are deeply conscious of the fact that there's this nonstop pull or this force that's pinning you to the ground. Having gone without it for a little while, you become a little more conscious of it. And of course, the acceleration that pins you to the ground is an acceleration of 1g. Do you guys remember what the value of little g is? That was from our earlier lectures on mechanics. Oh, I guess they tell you.
Yeah.
Never mind.
Would it be more correct to say negative 9.8?
It doesn't matter. Up, down, there's no such thing as up or down in space. It depends how you want to look at it. But yes, if you were doing a problem, Vladimir, then perhaps. For our intents and purposes, we can just call it 10 meters per second squared, okay? That's an acceleration of 1g. Imagine that some sinister aliens constructed a classroom that in every way resembled, well, I guess we're not in the classroom anymore, thanks COVID-19. So there goes that analogy. Imagine some aliens reconstructed your bedroom with faithful accuracy and, you know, painted some fake trees outside your window such that you were not quite aware that you were inside an alien spaceship. If they put some thrusters on this alien spaceship and they accelerated you through space at 1g, you would feel the floor crash into your feet with a force that was in every way identical to the force that you feel pinning you down to the ground. You would feel like gravity was at work because as far as you were concerned, your feet were stuck to the floor. And if you jumped, you could only get about, you know, this high or so before you came crashing back down. If you laid down in your bed, it would feel the same way. If you played a game of soccer, it would feel the same way. In that sense, you've constructed a kind of artificial gravity, which is not the true gravity of a planet, but an artificial gravity created by accelerating a spaceship forward through space. And you'd have to constantly be accelerating this spaceship and constantly firing those thrusters to maintain this illusion. In fact, there's kind of a cool old-fashioned 80s movie that has just this principle. If you guys want to try to watch it sometime, I love this movie. It's called Dark City. And in Dark City, the protagonist is a private detective, or Actually, he's been accused of murder, and he's traveling around this kind of Gothic nighttime city trying to figure out why he can't remember where Shell Beach is and all this other cool stuff. And only towards the end of the movie does he begin to realize that he's not actually in some Gothic city at night, but he's instead part of some elaborate alien experiment that mimics the effects of a real city. It's a totally ridiculous and fun movie that I think you guys should watch sometime. So go check out Dark City for an idea of how there's not a lot of good physics in it, but it's just fun. Okay. Einstein is a little bit ambitious here. He claims that even though the situation on the left is quote unquote real gravity, the gravity of a planet holding you down, and then the gravity on the right is an artificial gravity created by rocket thrusters, he goes on to claim that these two things are equivalent in any way, and that we should not distinguish between accelerations caused by gravity and accelerations caused by motion. This is the idea behind the principle of equivalence. There's also another way to formulate the principle of equivalence. And instead of considering gravitational effects, it's to consider what's called a free fall reference frame. In fact, this is where Albert Einstein famously got the idea for his principle of equivalence. Apparently, while he was working on this theory, there had been a bricklayer working on the 4th or 5th story of some housing complex nearby, and he had fallen 4 stories, presumably to his death, but as these things sometimes happen, he somehow survived, and the local newspapers interviewed him and said, "What did it feel like, Mr. So-and-so, when you fell off this building and you were falling to your death?" He said, "Honestly, I just felt completely weightless. I didn't feel any gravity at all." Einstein had a eureka moment after reading this newspaper article. He realized that if you were inside of an elevator and some sinister forces were to, say, cut or snip the wire that holds you to the building, you and the elevator would go into what's called a free fall reference frame. You might remember that one of the effects Galileo proved when he disputed Aristotle is that if you take two objects and they have completely different masses, they will both accelerate towards Earth at the same rate, or not rate, the same acceleration of 10 meters per second squared. I don't know if I showed this class or the other class, but Neil Armstrong famously reproduced those results. When he landed on the moon, he took a hammer and a feather, he dropped them in the airless gravity of the moon, and they fell to the ground at the exact same acceleration. Because you in the elevator must fall to the ground with an acceleration of 1g, during the time of your descent, you in the elevator will kind of be in a co-moving reference frame. It's not an inertial frame because it's accelerating, but as far as you're concerned inside the elevator, it is kind of an inertial reference frame because there's no relative motion with respect to you in the elevator. You're just kind of bopping off of each other. In fact, Einstein formulated the principle of equivalence in a way in which he stated that if you are in a freely falling reference frame and an elevator prevents you from seeing the gravity of a planet outside, in every sense, that is equivalent to the pure weightlessness of a man inside of an elevator floating in deep space, far from the gravity of any planet or star. Of course, when he hits the ground, the difference between those scenarios are going to become painfully different or obvious, right? But up until that point, he argues, they are equivalent from the point of view of physics. And if you think about it, it's a reasonable thing to say, but it's kind of a crazy thing to say, right? It's crazy to argue that an elevator, far from the effects of any gravity or star, are equivalent to a person falling to the ground at 1g. In any case, the principle of equivalence is similar to one of the postulates of special relativity. You have to listen to its craziness and consider it and see what the consequences are. And it turns out the consequences are important. One of the effects that you discover if you assume the principle of equivalence is true is that mass, gravity, has the ability to deflect and alter the path of light or photons. And let's do a little thought experiment that Einstein did to sort of demonstrate this. Okay, let's imagine a scenario kind of similar to one of the ones we did when we developed time dilation of two observers, one on a planet, painfully aware of gravity. We'll call that observer A. And a second observer will be in a free fall reference frame, an elevator that's been cut. And I'm going to draw that elevator at two different heights of its descent. Okay. So we'll make it 20 centimeters. By 15 centimeters. At least that's how it's going to be on my board. And I'm going to draw the elevator, if you guys can hear me, at two different stages of its descent. Sorry, I'm taking great pains to make sure these elevators are the same dimension and look the same. Okay, so what we have here is we have an elevator which has been sort of snipped by a giant pair of scissors not shown, okay? And it's in the process of undergoing a free fall acceleration at 1g to Earth. And inside, we'll put a weightless observer.
Excuse me.
That's okay. I'm deeply unhappy with my scissors here, so I'm going to work on those. Okay. There are your scissors. Okay. So the scissors have cut this rope, and the elevator is going to, those scissors are even worse than the ones I did before. All right, well, you know, they didn't hire me to teach you art, thank God. Let's perform a kind of wacky experiment similar to the one that we did in our other relativity exercises, where we simply fire a laser beam across the bottom of the elevator floor. So I'm going to have a laser beam, L, attached to the left side of the elevator, and I'm going to have a detector, D, on the other side of the elevator. It's going to be just a few inches off the ground. And what we're going to do is we're going to fire a red laser horizontally across the elevator, where it will be caught by the detector some distance h above the ground. If the principle of equivalence is true, the effects inside the elevator should be identical to the effects of an elevator floating in the vacuum of space, far from the gravity of any planet. In fact, weirdly, B is definitely not conscious of the fact that he's in a free fall reference frame near a gravitational field. It's only A who's aware of the gravity of the planet at all, because like most elevators, this one doesn't have any windows to look out of. Oh, wow. There's some craziness going on outside. Hold on. There's some kind of protest or something. It's far down the street, but a bit of excitement here today. There's some kind of a protest or something happening a few blocks away, so there are big drums going off in the background. Anyways, let's consider that elevator that's in deep space.
Go anarchy.
Pardon?
I said go anarchy.
Go join the protest? Is that what you said?
No, anarchy. Okay, actually, yes. Screw the lecture, go with an anarchy.
Anarchy, yeah. So if we perform this experiment in the vacuum of space, of course, the laser beam would fire unimpeded horizontally across the elevator. Forgive me if I'm going too slow here. I'm just trying not to trick anyone. And that means the effects of the person in deep space, the experiment should run the same whether you're in a freely falling reference frame or whether you are in deep space, far from the experience of any gravitational effects. However, A is aware that you are not in deep space, and the elevator is continuously falling, and of course, light has a finite travel time. It takes time for the laser to fire and for the laser to reach the other side of the elevator, no matter how small it is. Let's call this position the start time, and this position the end time of the experiment. How is the experiment to look to observer A? Inside the elevator, the laser has fired at this point, but both observers need to agree that the laser has been detected here at the end of the experiment. What will the path of the laser beam be for observer A? Not the same as B's. In fact, A will see the laser beam take a curved trajectory, what we would call a geodesic in geometry, and the laser beam will actually be bent and distorted during its fall from start to end time. There's only one difference between observer A and observer B. Observer A is conscious of gravity. And that means it is the gravitational field itself which is bending and altering the trajectory of the photon. Now that's kind of a wild idea because photons, as you've learned in your previous lectures, are electromagnetic phenomenon. They are not related to the gravitational force. Remember that,
Massless.
pardon?
They're also massless.
That's the problem, or that's the cool part of this, Vladimir, is that photons are massless. In fact, if you look too carefully at mass, you quickly discover that it's sort of an illusory concept, right? When you take your basic baby science class, some ding-dong like me holds up this 1 kilogram mass, this test mass, and says, this is a kilogram. This is what mass is, right? But as you learn a little bit more about science, you realize that this kilogram, its designation is arbitrary, and it's actually made up of aluminum with lead shot inside. And aluminum and lead are two elements from the periodic table. So you go poking around, try to find out where the mass is, and sooner or later you're confronted with the Bohr model of the atom, right? So let's go ahead and let's call up our lead atom. Not a lead atomic number, but just lead atom. Okay. And someone shows you a picture, the picture similar to what I did, of a lead atom that looks like this, with so many protons and neutrons inside and some electrons buzzing around. This picture actually kind of sucks, and it's a lie, because the electrons are quite small and quite tiny in comparison to the nucleus. There's also a crazy amount of space between the nucleus and an atom.
It's like sun and earth.
Or even worse. And it's not really easy to draw atoms to scale. That's why you never see them drawn to scale, because if you did, share screen whiteboard, to draw an atom to scale, the nucleus would be like this, and the electron cloud would be out here. And at that scale, you couldn't even draw the nucleus or the electron because they wouldn't be visible as anything more than dots compared to the radius of orbit. Okay, so now you're talking about mass, and you realize most of this fucking atom is empty space. And then you start looking at the particles themselves, and nope, it don't work. Because when you're told that something like this is a proton and something like that is a neutron, I mean, let's face it, we all know this. Balls are for slow children, okay? This is the kind of thing that we like to talk to people about because it's something that they understand. A stupid ball, it hits you on the head, you throw it down the street. But real particles, real pieces of matter, they're not particle-like. They have wave properties. Sometimes they can overlap each other, and sometimes they do uncomfortable things like tunnel through the sides of walls. And it turns out that the real mass Well, the real particle that you've been hunting for, this essence of, because you see what I mean, right? You assume that all the mass is in the protons, the neutrons, and the electrons, but then you start trying to look at a proton, and instead of it being like this, it turns out to look a little more like that. And now you're really not sure what the hell you're talking about anymore. So you just give up. You just say, I'm going to be too stupid to ever understand what mass is. In fact, I think I understand gravity better than mass, because when I fall down, it hurts, and that kind of makes sense to me. So you decide that from now on, you are going to define mass not as the stuff that's in the stuff, okay? But instead, you're going to define mass as the carrier of the gravitational force. In fact, you're more comfortable talking about the force of gravity than you are about mass. Mass is a carrier for the force of gravity. And electromagnetism is also a force. Do you guys remember what its carrier is? What would be the carrier? What would be the essence of electromagnetism that controls how much electromagnetic attraction or repulsion you have?
You're talking about the mediums, like waves are what are the medium for wave? Like air is the medium for sound waves.
I don't like this analogy. It's not how people talk about it. They talk about it as a carrier. It's the thing that controls the amount of force. The size of your planet controls it, or the mass of your planet controls its gravity, right? And to some degree, its radius. You guys don't remember what the carrier of electromagnetism is? You did a problem on this a couple of weeks ago. What makes the electron orbit the nucleus of an atom?
The attraction between the positive charge and negative charge.
That's it, Vladimir. The carrier of electromagnetism is charge. Charge, the amount of plus or minus that you have, controls the amount of electrostatic forces between things. You know your saran wrap? It's sticky. You can cover a banana with it. It's basically a sheet of rubber with extra electrons sprayed onto it. And those electrons hate each other. And in their desire to get away from each other, they will do anything, including hug a banana. Okay?
Yeah, going to such extremes.
So let's have some fun for a second. And remember how all this semester I wanted to show those kind of cool Java animations?
With Adobe something?
I finally figured out how to do them. Were you guys here for that? There's a picture of photons that I wanted to share with you all semester long. Physics Java apps. I think I can actually run them now. Let's see. Radiating charge. Come on, baby. Fingers crossed. We can do this. Fuck. Okay. Here. This. Look, I still have this one running, right? How did I do that?
Wait, can you go to files back to
radiating charge. Maybe it's because I did it from here. Let me try. Come on, come on. How did I do it before? Were you guys, was this the class where we figured out how to do this?
No, you just kind of magically popped it out.
No, I think it was the other class where we opened up some weird website. It was a Chrome plugin. That's what it was. So it was a Chrome plugin. I have the Chrome plugin. I think I have to hit this thing. Okay, I can't lose the day trying to figure this out, but it was weird. Like I used this Chrome plugin and I dragged, simply navigate to the open the Flash Player extension and click the Add button. Okay, so this is the radiating charge. This is the Flash extension and click the Add button. Huh. All right. I'm gonna drift wide of the point here. It was a really cool animation where you see that photons are electromagnetic waves. They're created by charges. It's very irritating. But basically, in the animation, you have a simple charged particle like a proton, and you visualize its electric field as a whole bunch of like spiderweb filaments emanating out from the electric field. Now, the electric field itself is not a photon, but when you grab the charged particle and you give it a wiggle, you make ripples or waves in the electromagnetic field. And that's what a photon is. A photon is ripples or waves in the essence of charginess. As Vladimir pointed out, photons being no more than ripples of an electromagnetic field, they don't have anything to do with mass. They're massless. And yet, what are we to conclude if the gravitational effects of a star can bend or alter the trajectory of photons? It means that gravity is capable of bending light. This seemed like a preposterous suggestion in 1915. And Albert Einstein went on to make a remarkable prediction. It's sometimes called the bending of starlight. There's a few other names for it. But let me show you a slide that demonstrates how it works. Einstein realized that if gravity could curve or alter the trajectory of photons, then you should be able to see the position of stars change when a massive object like the sun passes in front of it. Unfortunately, most of the time, when the sun is up, it's daytime and you can't see any stars. But there's one exception to that, of course. You guys can guess what it is, right?
Oh, this when moon
When moon blocks sun. What do we call that when moon blocks sun?
Yeah. Wait, Annie said it.
Come on, Amy, Andrew, don't leave Vladimir hanging. What do you call it when the moon blocks the sun? I'm going to go and give you guys all an F. You know that? If you can't answer this question,
Eclipse.
in a fucking eclipse. Okay, right. You guys are scaring the shit out of me. Okay. All right. Einstein predicted that if you were to go out during a solar eclipse when the moon perfectly blocks the sun and creates darkness, that it would be possible that the sun could be very close in angular position to a background star. He then predicted that the star's path of starlight coming close to the sun would undergo a bending or a warping that would cause the position of this well-known star to shift by a tiny number of arc seconds. And when I say shift their coordinates, I mean, remember right ascension and declination? Remember that the right ascensions and declinations of pretty much every star in the sky have been known for thousands of years. If you say Betelgeuse, I can tell you its declination is +5 and its right ascension is like 5 hours and 15 minutes. He predicted that the position of a star would deflect and shift by something like 1.4 arc seconds. And so a famous scientist, Stanley Arthur Eddington, went out to observe some background stars during an eclipse, probably half to prove Einstein wrong as much as anything else. Let's go ahead and look for the picture. Eddington eclipse. And this was in May of 1919, just 4 years after Einstein predicted that this effect would be happening. Now, it might not come across too well over the internet. because the star was very dim. Do you guys know what this is again? This is a layer of the sun. Do you remember what layer of the sun this is? This is kind of turning into
Corona.
the corona. Remember that the corona does give off visible light, so the observers had to contend with that. There is a small dot here. That was the original position of the star. Then there was a dot here. That's where the star was photographed during the eclipse. They overlaid the two photographs. The angular shift was exactly that calculated by Einstein theoretically, 1.4 arc seconds. After the publication of this photo, Einstein became an overnight rock star of physics. Any single person before him could have gone out and made this observation. If they had just thought to fucking look at the angular coordinates of a star during an eclipse, they could have discovered this experimentally, but they never even thought to do it. He predicted it theoretically, then they went out to take the photograph, and boom, there it was. This is considered one of the hallmark supporting pieces of evidence that Einstein knew what he was talking about. Mass bends the position of starlight. How cool is that? Of course, you can see where we're going with this, right? This is going to be very important for black holes because they're going to trap and bend starlight themselves at a more extreme degree. One of the reasons I can't work out a lot of the mathematics with general relativity with you guys is that it's at a mathematical complexity that's way beyond this class. Most exercises in physics that you need to do, even as a student, involve calculus, and sometimes they involve three-dimensional calculus, vector calculus, and another form of calculus called differential equations. There are calculus, and then there are levels of calculus beyond that. General relativity requires the use of a sort of 10 to infinity dimensional calculus known as tensor calculus. Tensors are large arrays of numbers that represent a field of gravitational forces. Even the seemingly innocuous equation, like probably Einstein's field equation, which are considered the most important equation in general relativity. This is a very misleading formula for students like you guys, because each of these numbers that you see here are not a single variable, but they represent giant matrices full of numbers that you have to contend with. Some of the matrices can contain hundreds of elements. Some of them contain thousands of elements. It gets a little head scratchy. I did put myself through a full tensor calculus GR course. My experience was sort of like that. I likened it to Mel Gibson's Apocalypto, but for math. If you've ever seen Apocalypto, the guy just gets in trouble and he just starts running throughout the whole movie for his life. And that's what the class felt like. It felt like a run for my life. All right, so, but you can do it. Let's describe what those field equations are trying to tell us and what this bending of starlight means. It means there's a new way to look at gravity. Let's take notes on it.
Wait, but does gravity bend the light itself, or does it bend the space around it so the light has to take that
Right.
path?
Well, either, yes, it's about bending the space, but it's still ultimately bending the light. So both are true, right? Let's contrast it to the old way of looking at gravity. So in Newtonian gravity, you have something like a planet, right? And you have a moon or a star. And there's some distance between them. And the two objects somehow miraculously know about each other. The planet feels a gravitational attraction to the moon. The moon feels a gravitational attraction to the planet, and it is instantaneous. In fact, Newton actually wrote in Principia Mathematica that he was concerned with this problem, and he came up with a classy Latin phrase for it, actio in distans, which means action at a distance. It basically means I'm making this shit up. The planet is instantaneously aware of the moon. The moon is instantaneously aware of the planet. I'm going to couch it in some classy Latin phrase that makes me sound like I know what I'm talking about. But in fact, it's just gobbledygook. He just thinks the planet and the moon instantaneously are aware of each other. So they called this action at a distance. Einstein realized this is not what the mathematics were explaining to him. In general relativity, gravity is a two-step action that Vladimir has suggested to us. Forgive my lame English here, but gravity is two steps, okay? The first is that mass, through the action of gravity, is curving or warping the very coordinates of space and time surrounding it. In fact, you'll remember that one of the consequences of special relativity that I presented at the very end of class was that space and time were kind of now connected to each other in what we would call a four-dimensional manifold. A manifold it's like a coordinate system. It's like a sandbox, okay? So mass curves or warps the coordinates of space-time around it. And as Vladimir pointed out, this is how we can affect the trajectory of photons. If this troubles you, remember that we've already seen that traveling at a constant velocity can alter the flow of time and the dimensions of space. We've experienced time dilation and length contraction already. Now we have mass doing it instead of velocity doing it. Hopefully that won't be too much more of a leap. The second step is that the curved coordinates of space-time alter the trajectory of objects around it. And they could be massive objects, or they could be things like photons, which have no mass. The trajectory of other masses or photons. Hell, particles, neutrinos, airplanes, jumbo elephants, whatever travels around your massive object is capable of moving through the coordinates of curved spacetime. Let's just say masses and photons, because I really can't think of something that's not a part of those two systems. Masses and photons that move nearby. To help with this visualization, it's popular to construct what's called the rubber sheet model of general relativity. I've got a couple of pictures for that to help you guys here. It's difficult to visualize curving four-dimensional spacetime. So what we often do is we cheat, and rather than attempting to show four-dimensional spacetime being curved, we imagine 4D spacetime as being kind of like a two-dimensional rubber sheet, a manifold, if you will, in which we've drawn a bunch of coordinates in a sort of grid that represent space and time. Usually the two-dimensional sheet represents maybe the x direction in space and the y direction in space. Usually you don't bother with the z dimension because it just becomes too much. And if anything, the up and down z dimension might represent the time coordinate. Here we have a massive object. A bowling ball isn't massive enough to seriously curve spacetime, but they're doing it for cartoon purposes. Usually you make the model in a classroom and you actually take a rubber sheet, you stretch it across the room, and you put a bowling ball in it to represent the curved warpness of space. And then you simply roll a smaller particle, like a little tennis ball nearby, and you can actually make the tennis ball go into an orbit. The orbit will be a Keplerian ellipse, and the equations of its motion are identical in every way to a gravitational orbit. It's kind of wild, actually. So you can see an orbit like the orbit of the moon around Earth as an example of the moon trying to travel in a straight line, but being deflected by the curved coordinates of warped space around Earth. In fact, sometimes there are some very lovely demonstrations of this at, have you guys ever been to the Boston Science Museum before?
Not sure, maybe, but
Geez, you
not
kids were
sure.
born one day and then there was COVID-19 and you've never left your bedrooms. Get out there. Virus be damned. You're going to have to explore this world. In the Boston Science Museum is really cool. There's all kinds of fun exhibits, but I really love the Mathematica section. And they have this demo there called the Gravity Well. Since you haven't been there, let me show
No,
you.
I actually don't think I've been there now.
The gravity well is considered to be a demonstration for general relativity for students of how curved spacetime can make a gravitational orbit. And I think there's one in Hong Kong that's pretty cool. They take this big plastic cone and they curve it with the same coordinates that spacetime is curving, that masses are curving spacetime. I'm doing really bad on time here. I got to get moving. I haven't even gotten to the black holes yet. And what they do is they take some ball bearings and they just push them at a deflected angle and watch them rotate around this curved plastic funnel. And the ball bearings, because they have such little friction, actually go into these perfect Keplerian orbits, just like comets or planets do. And you kind of watch them continuously orbit around. Now, in the case of this gravity well, there is a small amount of friction between the ball bearings and the plastic, so eventually the orbits lose energy and they do in-spiral towards the center of the funnel. But in outer space, where there is no friction between the curved coordinates of space-time and the object, the planet continues to do this motion in curved space-time perpetually. In other words, curvature is a perfectly valid description of gravity. That's what I'm, trying to tell you. Okay. Now that we know a little bit about general relativity, there are some consequences to this. The first people to sort of play around with the idea that it might be possible to create a structure from which light couldn't escape was a famous German scientist by the name of Karl Schwarzschild. And I think at age 21, he took Albert Einstein's full multi-dimensional tensor calculus field equations, and he calculated the construction of an artificial star whose gravity was so dense that no light could escape. Now, this was the only paper he published. It was a brilliant and seminal piece of work. He died a year later because he got shot in the trenches of World War I, so he never published another paper in his life. Ironically, the equation that he came up with ends up producing the same result as if you take Newtonian escape velocity and just set it to the speed of light. So it's a little silly. Honestly, yeah. So he writes this big elaborate paper. So let's see the cheat version of what Karl Schwarzschild did. And this is what's called the Schwarzschild radius. You guys had a little version of this. Okay.
Some people are just in a league of their own, like
Well,
Einstein.
it certainly was. So I think Karl Schwarzschild in 1916, I mean, like 1 year after Albert Einstein published this paper of general relativity, he used general relativity to derive the conditions of a compact star from which light cannot escape. And that means a black hole for anyone who's been paying attention or hasn't been paying attention. All right, let's consider our chapter 4 escape velocity formula. So we have an object. It has a radius. It's probably a sphere because nature just loves the fucking spheres, all right? And it has a mass. If it's a planet, if it's a star, it has an escape velocity. The escape velocity is the square root of 2 times big G times the mass of the planet divided by the radius of the planet. Let's go ahead and shrink its size down because it turns out that you need to have a very massive object and you need to make it very compact in order for these conditions to be met. We're going to set this equal to the speed of light, okay? The speed of light is a constant. 2 is a number that does not change. Big G is a constant that does not change. That means we have a mass and we have a radius. Carl Schwarzschild decided to solve it for radius. You square the speed of light. Then you switch the position of R and C, and you come up with a formula which is known in physics as the Schwarzschild radius. R sub S is 2 times big G times the mass over the speed of light squared. If you try to represent it in terms of solar mass units rather than MKS units, it's approximately equal to 3 kilometers per solar mass. So in other words, the Schwarzschild radius of our own sun is 3 kilometers. The Schwarzschild radius of a star twice the sun's mass would be 6 kilometers, so forth and so on. If you're 1,000 times the mass of the sun, 3,000 kilometers. The picture that we have of the Schwarzschild radius could be simply a star with a radius and a mass. But the idea is that if your gravity is so intense that light cannot escape, then the idea is that probably nothing can withstand the gravitational pitch, the force of gravity at that state. And that, in fact, the atoms themselves would collapse, their internals. Remember that in a neutron star, we pressed down hard enough on a bunch of iron nuclei that we jammed the electrons into the nucleus of the star. We jammed the electrons into the iron nuclei, and we created a giant ball of neutrons. I think I forgot to mention it in Tuesday's class, but neutron stars are not supported by electron degeneracy pressure. They are supported by neutron degeneracy pressure. It's the force of the neutrons not occupying the same quantum state that prevents them from self-collapsing. If you could construct an object this compact, one of the ideas, in fact, I should probably draw a dotted line around it, is that nothing would be able to withstand the gravitational pressure you were applying to your object, and the entire mass would self-collapse into a singularity of 0 dimensions. You guys know what I mean by 0 dimensions, right? I mean a fucking point. Something that has no length or depth or width. A point is not supposed to be real. A point is supposed to be an abstract concept. And yet, this Schwarzschild radius, this black hole thing we're considering, causes us to imagine that it might be possible to just smush something down forever and never let it stop. What would your black hole look like? It would depend upon whether you were capable of seeing in multiple dimensions or not. Let's start with the basic stupid picture, the picture that I showed you during your homework session and the one that I've been building up towards today. I've got this little green slide here, function F5. The Schwarzschild radius describes a zone around the black hole from which light cannot escape. But this is just a sort of invisible barrier. There's nothing really there. If photons are outside the Schwarzschild radius, they might get deflected and even be able to orbit around the black hole. But if the photon crosses the event horizon, the escape velocity becomes greater than the speed of light. And that means light itself will start to in-spiral, just like you saw those ball bearings do, and they will eventually collapse down onto the singularity. Photons cannot escape. In fact, it's kind of weird. I think at a distance of maybe 2 to 3 Schwarzschild radiuses, photons go into a perfect orbit around the black hole, just like the moon orbits Earth. If you could orbit a black hole at 2 Schwarzschild radii, you could literally look straight ahead and see your back, because the light coming from your body would be smeared out into a complete circle. Oh, and Vladimir, that's just the beginning of the weirdness. Let's try to imagine what a black hole looks like from the point of view of curved space-time. It's kind of like the ultimate Super Mario Brothers pit, you know, the one where you fall down and you never stop falling. In a normal star like the sun, you curve and warp space-time around you in a slight way, such that objects like Jupiter and Earth can go orbiting around you in a cute little circle. Neutron stars represent an extreme curvature of space-time. They warp gravity into a very deep well, which it is hard to get out of. Light can escape the surface of a neutron star, but it loses a lot of its energy. Remember, I told you it becomes gravitationally redshifted. You actually stretch out the energy of the photon. You stretch out the wavelength and you lose energy as the photons try to escape the well. But still, a neutron star represents a warped space-time that has a finite curvature. When you construct a black hole, you pretty much puncture a hole into the curvature of space-time itself. You create a gravitational well that stretches to infinity. There's sort of no end to it. And the curvature is so steep that not only can you not escape if you get too close to it, but light itself cannot escape. So this is the coordinates for what's called the Schwarzschild black hole, which is a non-rotating black hole.
Wait, can I ask something?
Yes.
So, so you said how a neutron star like stretches the photons, the photon waves. So would it be reasonable to say that the black hole just stretches them so much that they just whiff themselves out of existence? Because you said that like the photons, they have like some kind of limit. So if you go into radio waves after the infrared and continue to do longer and longer waves, at some point they're just kind of like,
yeah, in fact, that's a pretty cool way to look at it, Vladimir, and it's completely correct. Just so the other students understand, Vladimir remembers that photons have a wavelength and an energy, and the two are related to each other. The energy of a photon is Planck's constant times the speed of light divided by wavelength, or in other words, energy is inversely proportional to 1 over wavelength. So if you have a photon with a wavelength like this, and then you take a second photon with a wavelength like that, the longer wavelength photon has less energy. Vladimir's idea is that you stretch out the photon so much that you basically, if I'm quoting you correctly, Vladimir, you're basically imagining that you stretch out the photon so much that you sort of flatline it, you destroy its wavelength, and therefore
it lands infinity.
Yeah, it's an infinitely long radio wave, right? Yes, that's a perfectly valid way to look at it. Let's do one cute little I'm probably getting close to my time limit here. Oh, I'm almost there. I was going to make you do a calculation of the Schwarzschild radius. Let me skip that to tell you something more fun and more interesting. You guys remember at some point I told you guys about the conservation of angular momentum. Let's just go back to that concept for a second. In physics, there's a concept called angular momentum, and we use the letter L for it. I have a vague idea why, but I'm not going to get into it. And it's defined as the product of a mass times a velocity times a radius. You guys remember I did that jazzy little demo with the bicycle wheel where I showed you how I could get it spinning?
Oh, yeah.
Gravity couldn't tip it over, right? Okay, that was a fun day for me. I hope it was a fun day for you. Things that start spinning want to stay spinning. Now, the reason why planets spin, the reason why the solar system spins, and in some ways the reason why the galaxy spins, is if you start with a big cloud of matter, and it has some massive radius, which is like 100 light years, and you start collapsing it by a factors of hundreds and hundreds of times, even the tiniest bit of net rotation, just a few particles drifting a little more to the left than the right, will mean that as you collapse the radius, the velocity will have to increase, right? And so as you bring your solar system down and it starts to flatten into a disk, solar systems and planets tend to rotate because they were formed by collapsing a big disk of dusty gas into a much smaller radius. Even, for instance, consider our own sun. The sun is a sphere, and I pointed this out in our last lecture, whose radius is 700,000 kilometers, right? If you contracted it down to a radius of 3 kilometers, don't forget that the sun has a net rotation. We actually did a lab on this. Does anyone remember the rotation rate of the sun?
It's different for different locations, isn't it?
Yes, there is differential rotation, but the value at the poles and the equator are similar. I was just wondering.
I don't remember it.
Let's pretend this is the multiple choice test that you're not going to take.
Okay.
0.3 days, 3 days,
Isn't it
30 days.
25 or 25 point something?
Yeah, but what are the units? Is that Sabrina back there? Who is that?
Yeah, it is, Sabrina.
I still remember your voice, Sabrina. Very good. Sabrina, it is 25, but 25 what? Minutes, hours, days, years, eons? The units. One of the messages of this class is that units matter.
It's I forgot.
Yeah, I'll say 25 days. Yeah.
25 days.
Okay.
That means the velocity of a particle orbiting around the sun, like a sunspot, for instance, right? A sunspot has a velocity of the circumference of a circle is 2 pi r, and we'll divide it by the period. So 2 times pi times 300,000 kilometers over 25 days. Who knows the musical Rent? How many seconds are in a day? 86,400?
3.15 times 10 to the 7th.
That's the seconds in a year, buddy.
Wait, what did you? Wait.
The people who like that silly musical Rent know the number of seconds in a day because there's a song they have to sing.
Seconds.
I think it's 86,400, right? 20.
Yeah. Oh, yeah. It actually is. I now remember it. Yeah.
Okay.
I don't know the song, but I just calculated it so many times. I kind of.
Right. So let's figure out how many kilometers per second a typical sunspot is rotating. I'll do 2 times pi times 700,000 divided by 25 divided by 86,400. Huh.
That's quite fast.
2 kilometers per second.
Yeah, I was wondering why you wrote 3 instead of 7.
Oh, because I'm stupid. That's why. All right, let's try that again. 2 times pi times 700,000 divided by 25 divided by 86,400. I got 2. Did I type 7?
Wait, are you supposed to do it in MKS units? You did
doesn't-
type 7, yes.
It doesn't matter. I need to explain where I'm going. Okay, actually, I got 2 kilometers per second, right?
Yeah. Of course it doesn't matter. Jesus.
Okay. 2 kilometers per second is actually kind of zippy. Vladimir, if I contracted the sun down to a black hole, I would have to shrink its radius to 3 kilometers. And the mass that the sun contained would stay constant. In order to conserve angular momentum, what would need to happen to the velocity?
It would have to increase by a factor of
700,000 over 3, right?
yeah, like 2.
Which is 230,000.
Yeah.
That means if you were to shrink the radius of the sun to 3 kilometers, you'd have to increase the velocity of your star to 2 kilometers per second times 230,000, right? And you get 470,000 kilometers per second. Do you know what the speed of light is?
Oh, wait, hold up.
Yeah. What's the speed of light?
300,000 kilometers per second.
So in order to conserve angular momentum, if you could compress the sun to 3 kilometers, you would need to be rotating faster than the speed of light. Whatever. That's obviously something's not right there. Do you think there's any such thing as a non-rotating black hole? By what factor? By what
Wait,
factor
can a point rotate?
can a point rotate? I don't know.
Because like rotation is when you have a sphere and you mark a point on it and you track that point, but you cannot mark another point on a point.
All right, so this is my final point that I want to make in the class, and I've been building up to this, Vladimir, so forgive me. Forgive an old ham his theatrical tricks. It turns out that you can try to use the equations of general relativity and go beyond what Carl Schwarzschild did, and you can calculate how the curvature of spacetime behaves if your black hole rotates. And the solutions that you come up with, once you graph them.
Wait, did it have anything to do with the relativistic addition of velocities or something?
No. Well, not exactly. This is what the equations show us. When black holes rotate, instead of space-time being warped into a single infinite point, a poke or a hole in the fabric of space-time, that the coordinates of space-time continue to curve and wrap through a sort of funnel and terminate at some other position in space-time. This is what's known as the Schwarzschild throat. A rotating black hole is also known in science fiction circles as a wormhole. Now,
But it's very improbable. It's like most scientists will probably say that it's like, nah, not a thing.
No, most scientists believe that wormholes are probably real. But remember, when you look at a black hole from the outside, you cannot see past the event horizon. What a black hole would look like if you could approach it from far away in space. Hold on a second. I'm bouncing between two different slides here. As seen from the outside, a black hole would probably appear, well, maybe something like this, or maybe even something like this. You'd be able to see stars far away from it. But once you
all you'd see is a lot of light.
Huh?
I thought that all you'd see is a lot of light.
No, you see, well, light will definitely orbit or curve around the black hole, but once you get to the event horizon itself, the black hole is a perfectly dark sphere. It doesn't emit any light. It only captures light that gets close to it. You know, black holes don't, you watch the TV shows and the narrator goes, a black hole sucking everything in its path. Black holes don't suck things in unless you get stupidly close to them and you cross the event horizon. If our sun were to be collapsed into a black hole tomorrow, Earth would continue to orbit it at 1 AU with a period of 1 year forever. There just wouldn't be any sunlight and life would kind of be hard for us. But if the sun turned into a black hole, it wouldn't slurp up Earth and Venus and Jupiter. You can orbit a black hole just like you can orbit any star. If you get too close to 3 kilometers, then things are going to get unpleasant because tidal forces will become so intense that they will literally pull you apart molecule by molecule into a little puddle of atoms. So that's one of the troubles with going through, say, a wormhole is you'd have to figure out, first of all, how to get into it without being ripped apart by tidal forces. And the other problem with wormholes, in science fiction, people just fly through the wormhole and bam, you're in another galaxy or something, right? And it might be that the field lines terminate in another galaxy. That could even be possible. But the problem is, just as the escape velocity here is the speed of light, the escape velocity over here is the speed of light. You'd almost have to go faster than the speed of light to escape the wormhole. What would probably happen if you fell into one of these things is you'd be pulled apart atom by atom until your energy was subsumed by the black hole itself. Every time a rotating black hole or a wormhole devours a star or a planet, it absorbs the energy and uses it to increase the diameter of the rotating throat. So if you fell into a black hole, your energy would probably become part of the black hole itself, and you just expand and open the portal a little bit. Wormholes probably are real in the sense that most black holes probably rotate very rapidly. But from the outside, they still just look like a normal black hole.
Wait, but so what's more weight? So if the singularity is a point, so you decrease the radius infinitely, doesn't it mean that the black hole has to rotate infinitely fast? Like
Something like
not
that.
some
But it probably,
500,000 kilometers, but like literally infinitely fast.
when you mention the addition, the relativistic addition of velocities, something like that is going to happen. It won't actually surpass the speed of light, but they probably do rotate. The point that I was just trying to make, Vladimir, is I couldn't personally imagine collapsing something by that many orders of magnitude and not have it be spinning, because I intuitively understand angular momentum. I was trying to give you that same intuitive sense. That's all.
Oh, okay.
Okay, look, I've used up all the time for this lecture and all the time for this class, and obviously
Okay.
I'd like to do a little more. Feel free to sign up for my Astronomy 1010 course, offered both Summer 1 and Summer 2, to learn more about space. And in that class, I cover planetary science and show you lots of pictures of Mars and Jupiter and Neptune and so forth. So we always need fresh meat for the grist mill. It's a 4-credit lab science, just like this one, and you can transfer it to any school or university. So there's my pitch for 1010 if you need another lab science. Okay, we're going to take a short tea break where I furiously drink water. And I am going to select, I have some problems from chapter 19 that might not be appropriate, or maybe would, but I just want to select quick, easy, fun problems that demonstrate some cool aspect of black holes or general relativity. So let me fiddle around and pick those. And right now, cell phone time is 1:45, so we'll get going around 2 o'clock. Does that sound good?
Yeah.
I'll try to pick some easy problems that we can crank through fast, because I'm sure you guys have stuff you want to do today. So meet me right here at 2 o'clock, and we'll get into it, okay?
Did he take topology
Huh?
at college? Did he take topology?
No, I did not.
Oh,
I took
okay.
many mathematics, but not topology.
I know you just mentioned manifolds, and I immediately thought of topology. I was like
Yeah,
wondering if it took.
and some of the field equations are related to the things you'd study in a class like that. But usually when you're studying physics and astronomy, you don't have time to take all the mathematics that you actually need, because you also have to study the science part. So they just kind of teach you a few classes where they throw in a bunch of random math stuff. It's like a grab bag of math bits, and then you have to just sort of survive from there. That's kind of why physics is a badass science, because you're just supposed to figure it out for yourself at some point. It's kind of cool. All right, let me take a tea break and pick some problems, Vladimir. I'll be back. Okay, welcome back, friends. We're going to do our final homework of the semester, homework number 12. I was fiddling around trying to get that radiating charge flash app to work. If any of you are good at computers and can tell me how I can run this file, this is a simulation for a radiating charge. Let me put it into the chat box in case you guys can fiddle around with it while we're working. I have this browser extension that's supposed to let me play flash files, and I did get it working at some point, but for some reason I can't remember how I did it. This flash player extension, Chrome Flash Player. You're supposed to be able to navigate to a web page that has a flash file. And I'm supposed to be able to go up to this little tab and sort of see the flash file and hit it and play it from there. But for some reason, it's not working. Host to the web page, open the Flash Player extension, and choose from detected flash files. This is the website. This has the flash file, but it's not detecting it for some reason. And I'm not sure why that is. I've downloaded it even, but just nothing. Open. I'm not sure. All right. Anyways, I've on Blackboard, I've uploaded the new homework number 12, 4 problems from chapter 18 and 1 problem from chapter 19. One of them is about gravitational waves, which is kind of a hot topic in physics right now. That simulation would have been very helpful for describing that. I don't have it, and I have to come to terms with it. I didn't figure this out. Okay, Vladimir, help me set up this by reading me those problems again.
So it's chapter 18. 57, 58, 59, from 57 to 60 basically.
And from chapter 19?
53.
All right. This is homework number 12, our final homework. Don't forget to add your name. And of course, as always, this is Astronomy 1020. All right, why don't you read me chapter 18, number 57, Vladimir?
Chapter 18, 1857. The Crab Nebular Pulsar winds down.
Do you guys remember the Crab Nebula from our last lecture?
Yes, it's a very violent kind of nebula from the star that exploded.
From a type 2 supernova, right?
Yeah.
Crab Nebula. So this is a supernova remnant. So it was a large high mass star that underwent a supernova. It was not massive enough to form a black hole. Instead, the central core turned into a neutron star. And it's one of those particular types of rotating neutron stars we call a pulsar. Remember how the pulsar works? The pulsar works because the neutron star has a potent magnetic field associated with it, which beams radio waves towards Earth as the pulsar rotates. So we can measure the period of the pulsar's rotation by staring at the Crab Nebula with a radio telescope and looking for the blip, 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 blip that comes to Earth. All right, Vladimir, why don't you read that to us and I'll write down the givens.
All right. Theoretical models of the slowing of pulsars predict that the age of a pulsar is approximately equal to pi over 2, not pi, sorry, p over 2r, where p is the pulsar's current period, and r is the rate at which the period is slowing with time. Observations of the pulsar of the Crab Nebula show that it pulses 30 times a second. So P equals 333 milliseconds.
That's 33.3 milliseconds. Remember, Vladimir, milli is 1,000. If I move this 1, 2, 3, 33.3 milliseconds.
All right.
0.0333 seconds. That's a very rapidly rotating pulsar, right?
Yeah.
Okay.
but the time interval between pulses is growing longer by 4.2 times 10 to the negative 13 second with each passing second. So R equals 4.2 times 10 to the negative 13th second per second.
Second per second, which is actually unitless, right?
There's an accelerator. Oh, yeah, it is.
It's here's one of the fuckery of this problem. The reason
I
why I
was
think
gonna
it's
say that it's like an acceleration thing.
it's not an acceleration, it's a time rate. If you slow down by 1 second per second, for instance, you're changing the rate at which your period spins. Unfortunately, a change, a time rate has units of time per time or no units. It's a little bit goofy. That's one of the funny things about this problem. Anyways, keep going.
Using that information, estimate the age of the Crab Nebular pulsar. How does your estimate compare with the true age of the pulsar, which was born in the supernova observed in AD 1000 in year 1054 AD?
I don't know if you guys remember this from our lecture last class, but the Crab Nebula is a supernova that went off in the year 1054 AD. Do you guys remember who recorded this?
No.
It was actually ancient Chinese astronomers, probably at the Royal Observatory at Beijing. So supernova.
Wait, was it? So the year 1054, isn't it also the year when like the church split into Catholic and Christian? No?
Or you mean the Reformation, like Eastern Orthodox versus?
Yeah.
I don't know. So that's kind of funny. Are you suggesting that there was a supernova of religious proportions at work on Earth while there were supernovas of astronomical proportions in the
Totally.
sky?
I bet my.
I see no reason to doubt you. I just never really thought about that. From what I understand, this supernova was recorded by Chinese astronomers, and that's how we knew of its existence. We compared the coordinates of today's Crab Nebula with the location that the Chinese astronomers recorded the supernova, a new star appearing in the sky, and we pegged the actual year of the eruption to 1054 AD. It was probably a very bright star for a few weeks. All right, let's just plug into the formula and see what happens, okay? The suggested age of the pulsar, based on its period and its rate of slowing, is 0.0333 seconds divided by 2 times 4.2 times 10 to the minus 13. Since the units are seconds per second, I'm going to leave it as dimensionless. Why don't you plug that in and tell me what you get? This is a real easy problem.
God damn it. Hold up. Okay. Four basically. 4 to the power of 10.
2 sig figs would be helpful here.
Oh, okay. I can't do 2 sig figs because it's 3.96. So
okay.
one or 3.
You can do, it's 4.0 times 10 to the 10 seconds, right?
Oh, that's right. Okay. Yeah.
That's how you do 2 sig figs. Okay, Vladimir, let's convert that into years. What's our conversion?
3.15 times 10 to the 7th seconds.
Per year. So 1 year divided by 3.15 times 10 to the 7 seconds.
So that would be 4 divided by 1.3. So 1.27 to 1.3 times 10 to the third. So 1,300 years. No, 13,000 years.
13,000 years.
No, I was right the first time. 1,300 years. My bad.
Sure. Let's cheat, Vladimir. Let's keep 1270 years. I'm going to keep a little extra precision, okay? I know I didn't really justify it, but I'm cheating. Sometimes you can break the rules. Okay, so how are we supposed to compare this to the year in which the supernova went off, 1054 AD?
Well, I mean, 2021, minus
That's the idea.
1054.
So this pulsar supposedly formed 1270 years ago. So Vladimir is correct. To compare it to the current age, we would take the modern year of 2021 and we'd subtract 1270 years. And what do we get?
967.
And how does that compare? It's close.
But not really.
Well, it's off by 100 years. But I have to admit, normally when I do one of these problems, there's usually like a point, an overarching point. And I'm not sure what the overarching point is here. It might be that, well, it might be that I don't know enough about pulsars. It also might be that there's some additional physics that's at work there. Certainly the pulsar could not have formed before the supernova went off, and we know the supernova went off in 1054. So maybe there's something wrong with this model, but it's not like we got a wildly different number, Vladimir. It's not like we got 0 AD. You know what I mean?
Yeah.
It's out of 1,000 years, we were off by 100. That's what, 10% error rate?
Not too bad.
It's not too bad. Whatever extra details in there means extra physics that we haven't discovered yet, probably.
It's like 24% error.
Really?
Yeah. I mean, you divide what 967.
You do know how to do this, right?
Yeah, of course.
No, it's what I said. It's
Yeah.
8% error.
What? Oh, wait, of course. Yeah, never mind.
Remember, to calculate the percent error, it's the change in
the absolute value of change over
the answer. Your answer minus the true answer over the true answer, right?
So it's some BS. Just never mind.
So you're off by 1270 minus 967. Sorry, let me try that again. 1054 minus 967. You're off by 87 years out of 1,000 years. And that's 8% error, right? Not 24%.
Wait. Hold on. What?
Okay, to calculate your, if you really want to know, to calculate.
I didn't get the other part of that up there.
I'm going to write it again.
All right.
The percent error is your answer minus the true answer, absolute value, over the true answer. So the absolute value is 1054 AD minus 967 over 1054. And if you plug that in, you get 8% error.
Wait, but why? Wait, yeah, I'm big time confused. Why are you plugging in 1054 and not 1270?
1270 is the age of the pulsar.
Yeah.
but we're comparing the difference in date over the.
Oh, crap.
I played fast and loose here because I probably should have.
Oh, okay. All right, all right.
I should have divided it by 1270 or something. It doesn't matter. It's a low error rate. It's close to 10%. Look, you're clearly off by 100 years out of 1,000, right? I don't even know if that's fair. You know what, Andy? Don't worry about this. This isn't important. That and that are the only two parts of the answer you need. I consider that problem done. Man, I'm having a really weird day today. Let's just move on from there. Can I erase?
Oh, yeah.
All right. All right, 58. Who's going to read that? How crazy is it? Let me see what the problem set has for us. 18. Oh, great. Is this the one that's upside down for you guys too?
I mean, I have my textbook open.
I should save this. Okay. Go ahead. If you want to read it again, Vladimir, that's fine. It doesn't matter.
A water black hole. That's nice. Wait, are you ready to like?
Yep.
Okay. A water black hole. A clump of matter does not need to be extraordinarily dense in order to have an escape velocity greater than the speed of light, as long as its mass is large enough. You can use the formula for the Schwarzschild, hopefully I pronounced that right, radius, Schwarzschild, radius RS, R sub S to calculate the volume 4/3 pi r cubed sub S inside the event horizon of a black hole of mass m. What does the mass of a black hole? What does the mass of a black hole need to be in order for its mass divided by its volume to be equal to the density of water, 1 gram per cubic centimeter?
Okay. Let's explain the concept of what's going on here. Today in class, you learned that the black hole itself is technically thought of as a singularity, and it's surrounded by an invisible shield, a sort of empty sphere from which light cannot escape. Of course, the mass is probably concentrated at the center, and it's probably extraordinarily dense. But in a way, if you cannot see into this sphere, you actually have no idea what the physics is going on in there because you cannot make any observations to constrain your theories. It is literally just as valid for you to say that the inside of a black hole is full of cotton candy as it is for someone to say it's made of a quark star. There's no way you can discriminate between those two hypotheses because you can't gather any light and therefore you can't make any observations. The idea is, let's imagine what the density is. Imagine you filled this thing with water. How massive would it need to be in order to be a black hole? The volume of a sphere is 4/3 pi r cubed. And they suggest that we use the Schwarzschild radius formula for the radius of the, to find the volume of the event horizon, right? The volume of the black hole plus its surrounding sphere. So that would be 4 times 2 over 3 times pi. Oh, sorry. We've got to, all right, let's just do this slower by the numbers. 4/3 pi times 2 gm over c squared cubed, right? We need to distribute the cube to the 2, the g, the m, and the c squared. So what's 2 cubed, my fellow students? Do you know?
35.
Huh?
35.
What the shit are you talking about? 2 cubed means
Yeah, I'm messing with you. It's 8.
what? Were you doing that just to screw with me?
Yeah. I was messing with you. I was messing with you.
Amy, don't do that to me. Not in my fragile state today. Amy, what's the answer to that? Amy, I can't hear you because you're muted. Are you talking to me?
Yeah, I was. It's how did I forgot? I had it in mind.
2 times 2 is what?
8.
Oh, the whole thing is 8, right? Okay.
Yeah.
Fine. Okay, what if I cube c squared? What does that become?
C to the 6th.
That's right, 3 times 2 is 6, right? So therefore, the volume is 4 times 8 over 3 times pi times g cubed m cubed over c to the 6th. And 8 times 4, of course, is 32. I don't think 32 is divisible by 3. No. Okay, so 32 thirds times pi g cubed m cubed over c to the 6th. Now let's come up with the equation for density. Do you guys remember how density works? What's the formula for density?
Mass divided by volume.
Right. So do you guys know what to do here if you do mass over volume?
So we need to convert mass into grams.
No. Let's do that last. Let's do it theoretically first,
Okay.
and we'll plug in the
Okay.
numbers at the end. Do you see this equation for volume? If it's
Yeah.
at the bottom, we have to flip the whole thing upside down, right?
Yeah.
And we have to cancel out one of the masses. So what do I have then, Vladimir?
So you flip it. You get 3 30 seconds. Times c to the 6th over pi g to the 3rd m to the 3rd.
Not m to the 3rd.
M to the okay, second.
M squared, because we canceled out one of our m's with the top m, right?
Yeah.
You know what's interesting about this, Vladimir, from the point of view of proportionalities? The density of a black hole drops as the square of its mass. So supermassive black holes, ones that are hundreds or thousands of times the mass of our own sun, they're actually less dense than small, tiny black holes. And the tidal forces surrounding supermassive black holes are less extreme than the tidal forces around stellar black holes. Kind of a
I
weird.
think otherwise.
Huh?
I think otherwise, like it's more massive. You know.
That's what's kind of cool. It's not something you'd predict. Okay, now let's set this equal to the density of water. 1 gram per cubic centimeter. We should probably convert this to kilograms per cubic meter because we're going to plug all of those in MKS units, right? So how do we go from grams to kilograms?
So it's 1 over 1,000. 1 kilogram per 1,000 grams.
And then how do we go from cubic centimeters to cubic meters?
So it's 1 cubic meter per 10 to the 100 to the 3rd. What is this?
That's 10 squared cubed, right?
Oh yeah, of course. So it's 10 to the 6th per million cubic centimeter.
So these two cancel out. Million over 1,000 means you end up with the density of water being 1,000 kilograms per cubic meter, right? I've probably lost half the people here, but let's keep doing this. Okay. So up top, I'm going to solve for this. Let's just rewrite our equation. 3 over 32 times c squared over pi g to the third. The students are really hating me now. And that's all equal to 1,000 kilograms per cubic meter. Let's solve for mass. I'll flip the mass up and everything else down, or the 1,000 down. And I will get the mass should be the square root of 3 over 32 c to the power of 6 g to the third times 1,000 kilograms per cubic meter. This is our final answer before we sub in the values. Let's put a box around that. That's kind of important. This problem is a little more mathematically sophisticated than our average one. I kind of like it. Okay, so the mass then is, let's sub in the values, 3 over 32 times 3 times 10 to the 8 meters per second to the power of 6 over 7 times 10 to the negative 11 meters cubed per kilogram per second squared. All of that needs to be raised to the power of 3 times 1,000 kilograms per cubic meter. Y'all gonna hate plugging that in, so I'll do it along with you, okay? Do the square root at the end. 3 divided by 32 times speed of light to the 6th power, 3 e to the 8 raised to the power of 6, divide by 7 exp negative 11 to the power of cube. So I'll do shift cube out of laziness, divided by 1,000. And now I'll take the square root of that. 4.5 times 10 to the 38. Can someone else confirm that?
I'm doing my thing still because I was busy writing down your final when you plugged it in, so I'm calculating it still.
I'm sure the rest of you are hard at work calculating, right? You would never just sit there like mouth breathing, waiting for the answer to be delivered into your mouth like a little baby bird. No student would ever do that in my class. It'd be
Shift.
preposterous.
I think I will get the right thing. Square and yes. All right, let's go.
What'd you get?
I got the same 4.5 times 10 to the 38.
What are the units?
So kilograms.
So what should we convert this to make sense of our answer, Vladimir?
Oh, solar masses.
Hell yeah. How do we convert to solar masses?
Divide that by 2 times 10 to the 30th. So it's a little bit over 1 solar mass. Oh, actually, not a little bit, quite a bit. Never mind.
It's 8 orders of magnitude, right?
Yeah,
That's,
a little bit. All right.
that's 100 million, right?
Yeah. Never mind.
Y'all don't know your scientific notation, and it bugs me. All right. 4.5 exp38. You get about 230 million solar masses. There actually are black holes with masses comparable to this. One of the things we discover when we look towards the center of our own Milky Way galaxy is that there is a whole cluster of stars orbiting about an invisible point. Let me show you what the inner 1 light year of the Milky Way galaxy looks like. You can actually see it if you look at long wavelength infrared wavelengths. We refer to most stars in the galaxy are separated by 3 or 4 light years. This is called a nuclear star cluster. It's a whole clump of stars jammed into a box roughly 1 light year across. And you can actually study year after year the motions of their orbits. I think I have a little animation here. The stars are all on Keplerian orbits that are orbiting around some invisible point. And using Newton's version of Kepler's third law, you can calculate, based on their orbital periods and their distances, what the mass of the central object must be. The central object is an unseen companion, if you want to call it that, whose mass is somewhere between 2 to 3 million solar masses. And when we discovered this, we realized it must be possible to create supermassive black holes. Now, what's the most massive star you can think of?
So I watched a video and it said there was a star like 250 solar masses.
Yeah, there's a couple of weirdos out there, but usually in our class it was like roughly 100
Yeah.
solar masses with the top. Now, not all of the high mass star will turn into the black hole, only the central core. And at best, the central core can be no more than 50% the mass of the star. So I would expect something around 50 solar masses, probably closer to 30 solar masses, to be the absolute.
So you're saying, how did this happen?
Yeah. I can imagine how this happened. Can you imagine how this happened? Here's a hint.
Multiple black holes fused.
That's right.
No?
You had a whole bunch of stellar black holes, 30 to 50 solar masses. They were all on very tight orbits near the center of the galaxy, and they underwent what's called a black hole merger. 2 black holes in spiral. They do release some gravitational waves. We're going to see a problem on that in a moment. And basically, by swallowing other stars, the black hole grew its mass to the preposterous size of 2 million solar masses. Now, in our case, for a black hole to have the same density as water, it'd have to be 100 times greater than that. But there probably are galaxies out there that have such a thing there. The volume of the event horizon, or if you want to call it, or that sphere surrounding it, is so great that the density of them is actually quite low. The most dangerous black holes, the ones with the greatest tidal forces, are the small black holes, not the most massive ones. All right, let's move on. Let's see what 59 has in store for us. Do you want to read that one, Andy?
Yeah, I'll read that one. Energy of a supernova.
Actually, wait, Andy, sorry. Let me get queued up here. Sorry, buddy.
That's all right. You want me to pull it up? Oh, wait, no, I don't.
Yeah, energy of a supernova. That's what I want.
All right. Why is it not? Oh. I have to restart the page. There you go. Energy of a supernova. In a massive star supernova explosion, a stellar core collapses to form a neutron star roughly 10 kilometers in radius. The gravitational potential energy released in such a collapse is approximately equal to gm1/r, where m is the mass of the neutron star, r is its
GM
radius.
squared over r. Sorry, Andrew, it's GM squared over R.
All right. Where is it? Oh yeah. G equals, oh wait, yeah, GM square over R, where M is the mass of, oh, and
Where M is the mass of the neutron star, R is its radius, and big G, of course, is 7 times 10 to the negative 11 meters cubed per kilogram per second squared. So
is the gravity.
what they want us to do, it says here, using this formula, estimate the amount of gravitational potential energy released in a massive star supernova explosion. How does it compare with the energy released by the sun during its entire main sequence lifetime? So we need to have an idea of what a typical mass for a neutron star is. What would you guys, do you remember from our lectures what a reasonable guess for the mass of a neutron star is?
So the upper boundary of a white dwarf is 1.44, and the upper boundary of a neutron star is 3 solar masses. So between these two numbers,
Between
so like 2 solar masses.
I like it.
Two.
Let's say the mass is about 2 solar mass units. All right. If the sun's mass is 2 times 10 to the 30 kilograms, then that's about 4 times 10 to the 30 kilograms, because I doubled it, and 2 times 2 is 4. 10 kilometers, I don't even care right now, is 10,000 meters. It's 1,000 meters per kilometer, right? So let me just make sure we're reading this right. Yeah, we just plug in the mass and the radius, and that gives us an estimate of the gravitational potential energy. So the energy released would be 7 times 10 to the minus 11 meters cubed per kilogram per second squared. Notice I'm not messing around with 6.67. I don't really care. Times 4 times 10 to the 30 kilograms squared divided by 10,000 meters. Plug them and chug them, students.
Times 30 squared over 10,000. Should be about 1.12 times 10 to the 47th. No, not reasonable.
Say that again. Yes.
Yes.
1 times 10 to the 47. What are the units, Vladimir?
Kilogram. Oh, joules.
Joules, but 1 meter cancels and 1 kilogram cancels. It's kilogram meters squared per second squared, right?
Yeah.
And yes, that's the same units as kinetic energy, and therefore it's 1 times 10 to the 47 joules. Kind of a wild big number, right? The universe is only 10 to the 22 seconds long, so
10 to the 22 seconds long? What do you mean?
Do 10 billion times times 10 to the 17. Sorry, do 13.6 billion. Okay, maybe it's 10 to the 27 seconds, whatever. Anyways, they want us to compare this to the energy released by the sun during its entire main sequence lifetime. The sun will live for 10 billion years. And if we convert that to seconds, multiply it by 3.15 times 10 to the 7 seconds. This number is essentially 10 to the power of 10. So you get 3.15 times 10 to the 17 seconds. If I take the sun's luminosity and I multiply it by its main sequence lifetime, I would get 4 times 10 to the 26 joules per second. That's the luminosity of the sun. Multiplied by 3.15 times 10 to the 17 seconds. Seconds cancel. 4e26 times 4e26 times 3.15 exp7. I get roughly 1 times 10 to the 34 joules. What's the point?
Oh, so it's several. So it's like what, eight orders of magnitude.
13. That's 10 trillion times more energy than the sunlight emitted by the sun during its entire life. 10 trillion times more energy erupted in a moment than the entire sunlight emitted by the sun in 10 billion years. That's pretty wild, right?
Oh, 47, right. Oh, of course. Never mind.
That's because 47 minus 34 is 10 to...
Yeah,
I think I went a little too fast for you guys. Sorry, you can't keep up with me.
I can't see the bottom.
Or you can't even see the bottom. No wonder you can't keep up with me. You can't even see the board. 47 minus 34 is 13. 10 to the power of 13 is 10 times 10 to the 12. That's where I got that. I was just moving kind of quick. Oh, in case you don't know, why 47 minus 34? Because you're dividing 10 to the power of 47 by 10 to the 34. And that means you subtract the exponents. Whatever. It's a shitload more energy released in a supernova than the sun's entire lifetime of sunlight. That's the point of this.
No wonder it can rival the luminosity of a whole galaxy.
Yeah, they can be comparable to the nucleus of a galaxy or the bulge. Typically, supernovas of type 2 release about 1 billion solar luminosities of light. White dwarf supernovas do 10 billion solar luminosities. Andy, let me know when you're done here. Andy? Are you done?
What? Yeah, I'm done.
All right.
Tequila rose and chocolate.
Huh? Whoever said something, I don't know what the hell you were saying.
It's probably the background, in the background.
Oh, okay. Hey, Amy, will you read a problem?
Yeah, I read problem.
No, sorry, Andy, you read the last one. Amy, I want to hear Amy's voice.
Okay. Okay, it says energy of a black hole merger. Models indicate that the gravitational wave signal shown in figure 18.2 came from the merger of two black holes with masses of 29 solar masses.
Yep.
Or no, M sun and
Solar masses
36
is how you
M
say it.
sun emerged that results in the. Oh, okay. a merger that resulted in a single black hole with a mass of 62 solar masses. The difference in total masses between the star and finish of the merger corresponds to the amount of energy carried away in the form of gravitational waves.
Okay,
Use Einstein's formula E
Amy,
equals mc.
Stop for a second, Amy. Let's pause there. Let's pause at the difference in the total mass between the sum of these stars and this resulting black hole. The difference is carried away in the form of gravitational waves. Now, gravitational waves are something that we didn't get to talk about at this class because we sort of ran out of time. That was my bad. But gravitational waves are one of the predictions and one of the detections we've made that support the theory of general relativity. The idea is that if you have a massive object, as you guys saw in the previous problem, or in today's lecture, a massive object warps and curves the space around it. And if something forces that massive object to wiggle back and forth, you can actually make ripples in the gravitational field. Since I couldn't get that radiating charge demo to work, let's see if we can find a quick animation of what that would look like.
So it's the same idea as with ripples in the EM, like ripples in the charge.
Instead of rippling the electromagnetic field, you're now rippling the gravitational field. Let's see if we have a little animation of this here.
So the only dudes that can do this are like black holes or maybe neutron stars.
And in fact, they can only, well, technically anything can make a gravitational wave that has mass, Vladimir, but the gravitational distortions are so microscopic for most masses that our only chance of detecting them, let's try this, gravitational wave GIF. Let's see if there's like a little animated GIF here that we can grab.
Oh, I like this kind of sock.
This is sort of how it would work. If you have two spiraling, so anything can kind of make a gravitational wave, but the gravitational waves are such microscopic ripples in the curvature of spacetime. Only when you start whipping around a neutron star or a black hole or maybe a white dwarf could you actually notice the ripples enough to actually measure these gravitational waves. Now, try to understand, students, when I was an undergraduate and a graduate student, people weren't even 100% sure if gravitational waves existed because they couldn't figure out how to measure them. Some of the earliest people who tried to measure gravitational waves would take giant, massive steel rods and just sit there and stare at them with lasers to see if any gravitational waves might distort their length. And they knew the measurement was so small. Eventually, shortly after graduate school, they did figure out how to measure these things. And today, we actually have two gravitational wave experiments that have successfully detected gravitational waves. They are considered the highest precision science experiments made in the history of mankind. It's called LIGO, the Laser Interferometer Gravitational Wave Observatory. Basically, what they do is they construct these two really long tracks. They're about 4 kilometers long and they point in different directions, usually perpendicular to each other. Then inside the tracks, they have a really long laser tube. Let's see if we can find some better pictures of this. All right, so here's one of the LIGO tracks. One of them is in, I think it's in Virginia, right? This long tunnel or tube contains a vacuum that fires a laser and it reflects off of a mirror and bounces back. And they use the timing of the laser and interferometry to measure the length of the laser beam to a precision of something like 1 part in 10 to the 21. So the precision is basically like the diameter of a proton's width out of 4 kilometers. And they take these two laser beams and they continuously fire them and they wait for black hole mergers and neutron star mergers to send ripples through space-time that pass through Earth almost undetected, but they cause these lasers to fluctuate by roughly a proton's diameter out of 4 kilometers. And they do successfully measure these gravitational waves. And what the gravitational waves show is mergers between very massive objects. The two black holes kind of in spiral, and as they do so, the gravitational radiation gets more intense and you get a big burst. You can actually take the spectrum of the signal and superimpose it into the audio band, and they refer to it as the chirp. You can actually hear the oscillations of the two black holes. I wonder if I could find that. Gravitational wave chirp. They call it the chirp, and here we go. It's on YouTube. Hopefully you guys can hear sound from this. It's only a second or two long. Do you hear that? That's the
Yeah.
sound of two black holes merging.
Wait, is that so? Is it actually happening in the outer space? Like, if I were to observe it and not die, just suppose I could, I would hear this? Oh, wait, there's no air
There's
to
no sound
transfer the
space.
sound.
What you're actually measuring is an oscillation in the space-time coordinates itself. You're measuring ripples in space. Now, you can't actually hear anything in space because it's a vacuum.
Yeah,
But
yeah.
if you take the signal and superimpose it to air oscillations, as if you could hear outer space, you hear a chirp. I think it's valid. Some astronomers have actually likened this to normal telescopes allow you to see things in space with your eyes. Gravitational wave telescopes let you hear things in space. It's a totally different way of perceiving astrophysical phenomena, just like neutrino detectors. Okay.
Wait, so were these waves given some specific names? Because, like, photons are just waves as well. They're nothing but waves. So
Hold on, I'm sorry. I didn't understand your question.
Gravitons. Never mind. Well, like, photons are waves as well. They're just ripples.
Yes,
but they got a special name. We don't call them electromagnetic.
We call them gravitons, Vladimir. We do. There's a
There you go.
complete analogy between photons and gravitons. They're just different fields. One is the gravitational field, the other is the electromagnetic field. Anyway, back to the problem, right, Amy? This problem wants us to do something. Why don't you read us from here what it wants us to do?
Use Einstein's formula E equals mc squared to calculate this amount of energy. Be sure to put the mass in units of kilograms and the speed of light in meters per second, so that the resulting energy has units of joules. Compare your answer to the energy released by a supernova from problem 59 and to the energy released by the sun during its entire main sequence life.
Okay, so can you guys remember these two numbers, 29, 36, and 62?
Okay.
So we have a black hole merger. That's going to create gravitational waves. Like photons, Vladimir, gravitational waves also have energy. And we can calculate the energy using E equals mc squared, where this is the mass difference that is lost when the two black holes merge. After all, the original two black holes were 29 solar masses. Ah, shit, I can't remember the number. 29, 36?
Yeah, because you said 29, 36, 62.
The final black hole.
Oh, it became 62, okay.
But if you add 29 plus 36, you actually get
65. So literally three solar masses just got whiffed out of existence into pure energy.
Into warping the coordinates of space and time, and just ripples in space, ripples in the nothing. That's what's so crazy. They are literally ripples.
Can a person see the ripples in space itself?
There would only be one way to see them, Vladimir, as it explains to you in the Wikipedia page on gravitational waves. In order to see them, you would need to have a very potent and powerful signal. Where are we here? Let's do you would need to have a very powerful signal. And as gravitational waves pass through a set of test masses, just bear with me for a second here. This is what they do. There are two types of polarizations. If you had a whole bunch of tennis balls floating in space and your gravitational wave was strong enough, it would, if the tennis balls were arranged in a perfect ring, as the gravitational wave passed through them and the space rippled, it would cause the tennis balls, their coordinates, to stretch and shift like this. Unfortunately, even the gravitational waves from two black hole mergers are not a strong enough signal to do this to a ring of tennis balls. This is why we had to get crazier. And basically, this is the same thing, except instead of a ring of tennis balls, we have a laser beam, and we're waiting for the ripples in space-time to oscillate and shrink and stretch the length of the laser. Does that make sense? You can't see the gravitational waves because you don't have the precision of 1 part in 10 to the 21. If the signal was stronger, you would be able to see it. In fact, if you strong gravitational waves pass through your body, well, you're into molecular forces. Huh?
What would happen? So if I have like just a absolutely crazy, like what if it passes through the house?
No, because gravity
wobble?
Gravity is a shitty force, okay? It's not strong.
Yeah,
the ionic bonds and salts, the intermolecular bonds of your body are totally more powerful. So they can't wiggle your bones. Only if you were a ring of chargeless tennis balls in space could they wiggle you. Anyways, why don't we convert this to MKS units? 3 times 2 times 10 to the 30 kilograms is obviously going to be 6 times 10 to the 30 kilograms, right? And now we're going to plug this into E equals mc squared. The energy released is 6 times 10 to the 30 kilograms times 3 times 10 to the 8 meters per second squared. That's a U job, students.
Hold up a second. E 6 times 10 to the 30 kilograms times 3 8 meters per second. Okay.
What you get?
A squared.
9 times 10 to the 16. 9 times 6 is 50.
Oh wait, of course. I didn't even have to do that. So 54, 16, 46, and 554. So it's 5.4 times 10 to the 47th.
Yeah. Units?
Joules. Yes.
How does that compare with the energy from our last problem?
So it's like 5 times more than the supernova type 2 explosion.
Or to within the same power of 10.
Yeah, within the same magnitude. Yeah.
Roughly same order of magnitude as a type 2 supernova. Right?
Yeah.
That's kind of cool, Vladimir. That means 2 merging black holes are kind of the energy equivalent of a supernova. This is one of the reasons we are able to detect them from great distances away. And yes, they do propagate at the speed of light. So normally these black hole mergers aren't even happening within our own galaxy, Vladimir. They usually happened millions of years ago, but we're just catching up to the gravitational ripples today.
Wait, why do they move with the speed of light?
Because nothing can move faster than the speed of light, and energy propagates at the speed of light. In fact, do you want to know how they get the direction of the merging black holes? There's actually 2 LIGO interferometers. One is in Virginia, and the other is in Washington. And sometimes one detector gets the ripples first and the other one gets it second. And based on the time lag, they redirect which direction in space the black hole merger is coming from. Pretty cool, right?
Is like the difference in distance over the speed of light, right?
It's a short distance between those two facilities, but it's calculatable. It's a very high precision experiment. Okay, that's 60. We got one problem left. I'm going to erase this, everyone. Last problem of the class.
It's pretty interesting how to an outsider, it's kind of meaningless.
Well, I guess it's up to you to make your own meaning then, isn't it?
Yeah.
All right. I'm going to read the final problem because you guys have been such good sports. I had to take a photograph of it.
Wait, I can read it.
Okay, yeah. Actually, that's better because then I can write. So it's a JPEG. Can you call that up?
Okay. Yeah. I was gonna open my own textbook, but yeah.
Oh, sure. Whatever you want to do.
It's 53. Mass of the central black hole. Suppose mass of the central black hole. Yeah. Suppose you observe a star orbiting a galactic center at a speed of 1,000 kilometers per second in a circular orbit with a radius of 20 light days. Calculate the mass of the object the star is orbiting.
Okay. Normally, students, when we use Newton's version of Kepler's third law, we put it in terms of a distance and a period. But there is a way for us to rearrange it so that we can consider the radius of orbit and a velocity. It's known as the Orbital Velocity Law, kind of a lame name. And it tells us that the mass included in this radius r is v squared times r over big G. Pretty simple formula.
Orbital velocity law. Okay.
It's basically just NK3 for dummies.
Okay.
Let's convert to MKS. What's the velocity of 1,000 kilometers per second in MKS units?
1 million meters per second. It's 1,000 meters per 1 kilometer.
How about 20 light days? Let's see who can handle that.
So we can convert to light years and then divide that by 365, right? Yeah. Would that work?
I think.
Yeah. So
you know how I would do it, Vladimir?
how?
I would come up with the equation for a light day will be the distance that light can travel in a day, right?
Yeah.
So,
speed of light times 86,400.
one light day, LD, would be the speed of light times the time in a day. So it would be 3 times 10 to the 8 meters per second. And earlier in today's class, we talked about the number of seconds in a day. Do you remember what it was?
Yeah, 86,400.
As any fan of the musical Rent knows. So what's a light day then?
2.6 times 10 to the 13th. What am I talking about? Kilometers.
Nope.
Meters. Jesus.
Yep.
Okay.
Okay, so 20 light days times 2.6 times 10 to the 13 meters per light day would give us what?
V
5.2 times 10 to the 14.
is 2.6 exponent 13 divided by 7 negative 11. So it's what is going on?
What
I'm
is going
confused.
on? I'm lost.
I got lost for a second. 20. Oh, okay.
I just wanted you to multiply 20 by 2.6.
Yeah. I was already plugging it in. I was like, what is going on?
Jesus Christ, guys,
You're
we all
talking about
sing the
something.
same hymnal here?
Huh?
Let's stay together.
Yeah.
Okay.
Because one
I just want-
exponent of 6. Yeah.
We're devolving. Our final problem set is just dissolved into mush. Okay. Is it true that this times this is that? I just want.
Yeah.
Okay. I'm going to erase all this and we're going to plug it into the orbital velocity law. The mass of this unseen supermassive black hole is 1 times 10 to the 6 meters per second squared times 5.2 times 10 to the 14 meters divided by 7 times 10 to the minus 11 meters cubed per kilogram per second squared.
Yeah. Gravitational constant is so stupidly awkward.
That's because gravity is a stupid force.
5.2 exponent 14 divided by 7 so negative 11. So we got 7.4 times 10 to the 36th.
What?
A little bit of thinking here. So cubed, that cancels out. Second, oh, kilograms. Never mind.
Right. How many solar masses is that?
7 million. Oh no, like 3.5 million.
3.7 million solar mass units. Wow.
Pretty good.
That's what we call a supermassive black hole. For the final point in our class, a famous radio observation made 2 years ago attempted to, for the first time ever, to directly image the supermassive black hole in the center of the galaxy. They were not able to do it because, well, what would the event horizon of such a thing be? You guys remember that the Schwarzschild radius is 3 kilometers for every solar mass black hole. So the Schwarzschild radius of such a thing would be, I don't know, 3 times 4 is 12. So 12 million kilometers. That's less than an astronomical unit, right?
Yeah.
An astronomical unit is 150 million kilometers. We do not have sufficient angular resolution to image something 0.3 AU at a distance of 30,000 light years from the sun. But guess what? It turns out that there's a bigger galaxy that has an even more massive black hole with a larger event horizon, and it actually works out that we were able to image this in a galaxy in the Virgo cluster, I believe. This is Messier M87. Up to now, I've mostly shown you guys spiral galaxies, but there are other types of galaxies called ellipticals. Ellipticals are kind of boring to look at because you can't resolve the individual stars, so you just see kind of a smear of fuzzy light. And elliptical galaxies have no gas, so there's no dust and nothing cool to look at. Basically, what's really going on is you're seeing like a beehive of stars. Think of like a globular cluster. There are just stars rotating in every old crazy way, but all the starlight is kind of smeared out. Can you guys see this little jet there?
So
That's
it's
a big
quasar.
yeah, there's some kind of active black hole in the center there. That jet, I don't know if you would consider it a quasar or not, maybe an active galactic nucleus. But this jet is coming from the central black hole in M87. 2 years ago, using all the world's radio telescopes combined to make a giant radio telescope the size of Earth, we imaged the supermassive black hole at M87. Where's the iconic and legendary picture of it? I just had it a second ago. Here it is. This is a real photograph taken at radio wavelengths. I never thought I'd see anything like this in my entire life. You can actually see the event horizon where light cannot escape. And you guys, of course, know what this is, right? What is this?
Accretion disk.
It's an accretion disk. So this is not only the first ever image of a supermassive black hole, or any kind of black hole, it's also the first image of an accretion disk. And they yeah, because I don't think there are any other such. I mean, you can see them as X-ray point sources, but no one ever resolved them. It's very hard to resolve things at X-ray wavelengths.
Yeah, that is actually a fraud. I think it's just an overcooked donut. Oh, BS.
I'm starting to think that I might have overcooked your donut with all of this craziness. But
yo, for real, with today's lecture, I'm just getting after the general relativity, I just get lost in the numbers. I'm like, yo, what is going on?
I kind of wanted our final day to be full of crazy wackiness, okay? Culminating at the supermassive black hole at the center of our galaxy. Okay, guys, I think you learned a lot of stuff today, or at least I hope you did. And I hope you had fun learning it. And, you know, I'll be teaching these courses this summer, and I'll be teaching them in person in fall. And let me tell you something. The observatory, the Margaret Jacobi Observatory on the CCRI campus will be open come fall time. So I hope that some of you will come pay me a visit in IRL, as the kids like to say, and come look through my telescope, and I will show you some cool stuff. I'll show you binary stars and globular clusters and the ring nebula, and you're going to love it. All right. You can bring your friends, your dad, your kid brother, your boyfriend, your girlfriend, whatever, your dog, if they don't bite. Anyone's welcome to the observatory. And taking a look through a telescope is a special thing. So I'd like to be able to show that to you guys at some time. Vladimir, you and I have a research project to do this summer, so you're going to get a shot at that sooner rather than later. Okay, guys, I hope you enjoyed the class. Please submit the homework in the lab. I'm going to try to have the grades all wrapped up by Monday or Tuesday, so please adhere to that Sunday deadline. Once the class ends, I'm submitting the grades, and then it's pina colada time, okay? Several pina colada times, over. 10 to the power of 6 pina coladas is how many I'm going to have. And I'm going to be sitting on a beach with my head in the sand. I'm not going to know which way is up, and I'm not going to know that you didn't turn in homework 12 because the class will be over. So you need to get that homework in by this weekend, okay? You understand my point, I hope. Anyways, it was a lot of fun hanging with y'all. Thanks for being here. Andrew, 2 semesters with you. That was really awesome. Hope you get to make it to the observatory and hang out sometime, okay? All right.
So where is the observatory that we're going to use?
The observatory is at the CCRI Warwick campus, which some of you may not have even ever been to, right? Because some of you might be like Rhode Island Promise students that have never even left your bedrooms. But when you come up the main entrance to CCRI, I'll show you a picture of it here. When you're coming up, it doesn't quite look like this anymore, but when you're coming up the main entrance, you can actually see it in this image. Before the temporary parking lot, there's a street that goes right down there. And if you follow it down a few hundred yards, you'll see a little sign, and there's a forest glen, and it says Margaret Jacobi Observatory. And there's like a dome, a big metal dome with a telescope inside. So it's really, you can literally walk from the building to the observatory in 2 minutes. So it's a very short walk, or you can drive. There's some parking spaces down there. So at some point, Vladimir, you and I are going to meet up down there to try to get the old rust bucket working again. All right. And the rest of you, once it's all greased up, I want to see you come by and take a peek at that telescope. Okay. Hope you had fun. Go forth and thrash. I will see you guys around campus sometime. Okay.
Thank you.
Bye. Bye, Sabrina.
Bye.